Okay, lesson 3.2 is maximum and minimum on an interval. The goal of this lesson is to apply the derivative of a function to determine the max and min points on any given interval. So we are going to use the knowledge we obtained in chapter 2 in finding derivatives of a function in order to find values that are maximum and minimum on any given interval. So I've drawn a diagram here of a quartic function with a positive leading coefficient. It's positive since we are opening up, and I've labeled a few points. So we have a local min, a local max, and an absolute min. The absolute minimum is the smallest function value in the domain, and the local minimum is the smallest function value in an open interval in the domain, and a local max is the largest function value in an open interval in the domain. The steps to finding a max and min on an interval include, so taking the derivative of the function f of x and setting it equal to 0. Once we know the points, the x-coordinates of where our function equals 0, we need to solve the y-coordinates by taking that x-coordinate and plugging it back into the function. Once we've solved for our y-coordinates of those critical points in the interval, we're then going to solve for the y-coordinates of the two endpoints. Step 4, based on the y values we found, determine the maximum points in the interval. So, for example, in this case, we have one endpoint on the interval over here, one endpoint over here. We'll take these two y values, as well as the y value of this critical point and this critical point, and from there we can see which one is the greatest and which one is the least. So in this particular case, we know that on this interval, the max would be this point, and the minimum would be this point. Example 1 says, given the function 2x cubed minus 3x squared minus 12x plus 1, find the max and min values on the interval x is any real number from -2 to 0, and sketch a graph of the function. So f of x equals 2x cubed minus 3x squared minus 12x plus 1. So to find the derivative, we'll use the power rule. So we'll bring the 3 down in front of the 2. So we'll get 6x, decrease the exponent by 1, so 6x squared, minus, bring the 2 exponent in the exponent in front, minus 6x minus 12. So now what we will do is set the derivative equal to 0. So the first step we can do to finding the x values at which the derivative is equal to 0, we can factor out a 6. So we factor out a 6 and we're left with x squared minus x minus 2. We can factor that to x minus 2 and x plus 1. And we can see that when x is 2, the derivative is 0. And when x is -1, the derivative is 0. X equals 2 is not in the given interval. However, x equals -1 is. So for this particular case, we are going to find the y-coordinate for x equals -1, as well as the y-coordinates for the endpoints, x equals -2 and x equals 0. And then from those 3 points, we'll be able to find our max and min on the interval. So f of -2 is -3, f of -1 is 8, and f of 0 is 1. So by looking at these 3 y values, -3, 1, and 8, we can see that the least number out of all of these is -3. So therefore, f of -2 is the minimum on this interval, and that occurs at the endpoint. The max in this interval, however, is f at -1. When x is equal to -1. This is because the y value is 8, and this is the greatest out of all 3 numbers. Lastly, the example asks us to sketch a graph of the function. So to do that, we will also be using this value, x equals 2, because we know at x equals 2, we have a slope of the tangent that equals 0. So we can plug in 2 into our function. So when we plug in 2 into our function, we get 2 and -19 as our point. So the first thing we're going to do when we sketch it is we're going to plot that point 2 and -19, and we know that the slope of the tangent at that point is equal to 0. And -1 and 8, the slope of the tangent is also 0 at that point. We're going to plot that point. And since this is a cubic function with a leading coefficient that's positive, we know that it's going to start in quadrant 3 and end in quadrant number 1. So our function will look something similar to this. And that includes example number 1. Example number 2 says, a boat going across the lake uses gasoline at the rate of R of x equals 1/4 multiplied by the brackets 4900 over x plus x, where x is in between 30 and 120. X is in kilometers and R of x is in liters per 100 kilometers. Fuel costs $1.15 per liter. What speed will result in the lowest fuel cost for a 200-kilometer trip? What is the lowest total cost of the trip? So the first thing we're going to do is we will take the function r of x and we will find the derivative using the product rule. So the derivative of the first in this case happens to be 0. So in order to find the derivative, we will just take the first and multiply it by the derivative of the second. So 1 over 4 stays the same, and the derivative of this, 4900 over x plus x. X being brought to the numerator can be represented by x to the negative 1. So if we bring that negative 1 to the front, we'll get negative 4900 x to the negative 2 in the exponent plus 1, which is the derivative of x. We can now bring x to the negative 2 in the denominator, and we can conclude that our derivative is r prime of x equals 1 over 4 times negative 4900 over x squared plus 1. The next step is to set this equal to 0. So setting equal to 0, we get 4900 over x squared equals 1. X squared is equal to 4900, and x is equal to the root of 4900, which is equal to plus or minus 70. Since this is distance, we have to only look at the positive value, so x is equal to 70. So next thing we're going to do is we're going to plug in 70 into the function, and we get 35 liters per 100 kilometers. We plugged in our endpoints 30 and 120, and we got 48.3 and 40.2. So for a 200 kilometer trip, we're burning 70 liters. 70 liters at $1.15 per liter is 70 times 1.15, which is 80.5. So therefore, a speed of 70 kilometers per hour will result in the lowest fuel cost of the trip, and the lowest total cost of the trip is $80.50. Example number 3 says, in a certain manufacturing process, when the level of production in dollars is C of x equals 3000 plus 9x plus 0.05x squared, where x is in between 1 and 300, what level of production x will minimize the unit cost u of x equals c of x over x? So we're given the function u of x equals c of x over x. We know that c of x is also given to us, so we can plug this function into u of x. So now we have u of x equals 3000 plus 9x plus 0.05x squared all over x. So to differentiate this function, we will be using the quotient rule. So the bottom times the derivative of the top, subtract the top times the derivative of the bottom all over the derivative of the bottom squared. So that leaves us with x times 0.1x plus 9 minus 3000 plus 9x plus 0.05x squared. And we're leaving this term by itself as the derivative of the bottom is 1 all over x squared. So the next step would be to distribute x into the brackets. So we have 0.1x squared plus 9x minus 3000 minus 9x minus 0.05x squared all over x squared. If we simplify, 0.1x squared minus 0.05x squared is 0.05x squared. Plus 9x minus 9x will cancel out, and we're left with minus 3000 all over x squared. So for critical values, set u prime of x equal to 0. So 0 equals 0.05x squared minus 3000. 0.05x squared minus 3000. X squared is equal to 60,000 because 3,000 divided by 0.05 is 60,000. And if we take the square root of both sides, we will get x equals the root of 60,000, which is approximately 244.94. And since this must be a whole number as it is a production level, we can round that to 245. So therefore, a production level of 245 units will minimize the unit cost.